A robotics company just demonstrated capabilities that could completely reshape what we expect from humanoid machines. Matrix Robotics released footage of their Matrix 3 humanoid performing 6 features that blur the line between programmed automation and genuine intelligence. Let's watch the footage first. Now, let me walk you through each feature and explain why engineers are paying very close attention to what Matrix just revealed. Feature 1. Natural language commands without scripts. The demonstration starts with a human giving a verbal command: pick up the orange and the peach. No button press, no touchscreen interface, just spoken language. The Matrix 3 processes the instruction and begins moving. This is a multi-step process requiring the robot to accomplish several cognitive tasks simultaneously. First, it must identify which object is the orange. This requires computer vision capable of distinguishing between similar shapes and colors. Then, it must locate that orange in 3-dimensional space. Distance, angle, height, all calculated in real time. Next, it repeats the entire process for the peach. Identify, locate, plan approach. While executing these tasks, the robot moves its 27 degree of freedom hands slowly and deliberately. Each finger adjusts independently. The grip adapts to the shape and texture of the fruit. Too much force crushes the object. Too little force drops it. The robot must fingertips. Matrix integrated their system with a large-scale spatial perception foundation model. This allows the robot to understand not just what objects are in the scene, but where they exist relative to each other and relative to the robot's own body. The company is using Matrix's proprietary Wave Physical Intelligence model to coordinate these movements. The result is a robot that does not simply follow pre-programmed routines. It interprets instructions, perceives its environment, and generates actions on the fly. Feature 2. Tool use and adaptive manipulation. Next, the robot faces a different challenge. A puddle of water sits on a surface. The human does not give instructions. The robot observes the situation and determines the appropriate response. It identifies the water. Then it identifies a soft cellulose sponge as the correct tool for the task. Here is where the complexity escalates. The robot must form its fingers around the sponge with precise calibration. Apply too much pressure and the sponge compresses completely, losing its ability to absorb water. Apply too little pressure and the sponge slips from the grip. The robot uses its fingertip sensor array, capable of detecting as little as 0.1 newtons of force, to maintain the perfect grip. Then it uses the sponge to clean the water. This requires understanding how a sponge functions. Steps humans learn through physical experience. The Matrix 3 is demonstrating the ability to apply similar understanding through its AI-driven perception and manipulation systems. Feature 3. Contextual awareness without commands. The third feature might be the most impressive from an artificial intelligence perspective. A human sneezes. The robot receives no verbal instruction, no gesture, no input of any kind. Yet, it determines the appropriate response autonomously. The robot locates the XYZ coordinates of a tissue box. It approaches. It grabs a single tissue with as little force as possible to avoid tearing the delicate paper. It pulls the tissue out. It hands the tissue to the human. All of this happens because the robot understood context. A sneeze implies a need for a tissue. That inference required embodied chain of thought processing. This moves beyond executing commands. This is a machine observing a situation, inferring human needs, and taking initiative to assist without being told. That capability represents a fundamental shift in how robots interact with people. Instead of waiting for instructions, the robot anticipates needs and acts proactively. Feature 4. Non-verbal communication through gesture. The fourth demonstration shows the robot responding to a pointing gesture. The human simply points to a cardboard box. No words, no explanation, just a finger indicating direction. The robot interprets the gesture, identifies the target object, and retrieves it. The robot determines to use just one hand for this task. It opens its fingers by about 30 degrees. It applies approximately 0.2 newtons of force. just enough to grip the cardboard without crushing the material. Then it hands the box to the human. The entire sequence demonstrates visual understanding of human body language, spatial reasoning to locate the indicated object, and physical intelligence to handle fragile materials appropriately. Feature 5. Bimanual coordination for delicate tasks. For the fifth feature, Matrix demonstrates something deceptively difficult. The robot picks up an egg and transfers it into its other hand. The entire task takes about 30 seconds. This requires coordination between both arms, precise force control to avoid breaking the shell, and continuous sensory feedback to adjust grip throughout the transfer. The robot accomplishes this using three-dimensional woven biomimetic skin. Flexible fabric covers the robot's chassis and acts as a distributed sensing network. This skin cushions contact and detects impact forces in real time. When the egg touches the palm, sensors register the fragile shell. The robot adjusts its grip pressure instantly to accommodate the delicate object. This biomimetic approach mimics how human skin provides tactile feedback across the entire surface of our hands and arms. Feature 6. Multi-robot collaboration. The final demonstration involves two Matrix, 3 robots working together. One robot passes a box to the other. The task takes about 1 minute and 45 seconds. This coordination requires both robots to understand their shared goal, communicate their positions and intentions, and execute synchronized movements without colliding or dropping the object. Dual robot coordination opens possibilities for tasks requiring more capability than a single humanoid can provide. Assembly operations, large object manipulation, redundant systems for critical tasks. The ability for multiple robots to work together without human oversight dramatically expands the range of applications these machines can handle. Matrix Robotics priced the Matrix 3 at $99,000 for outright buyers and is introducing a robot-as-a-service subscription framework for early access partners. The company targets a manufacturing capacity of about 10,000 units to start, positioning them as a serious commercial player. Meanwhile, Unitree Robotics is pushing voice-driven arbitrary action with their G1 Humanoid, which listens to voice commands and executes them in real time. A person tells the robot to jump in place and then do a plank, and the robot processes the instruction, computes action trajectories, and performs the movements. Unitree filmed the entire video in one take, suggesting these are live responses rather than pre-programmed animations. While the immediate applications might seem trivial, the underlying technology has profound implications for service industries, logistics, healthcare, and potentially military operations. Beyond terrestrial robotics, Swiss startup Orbit Robotics announced Helios, a specialized humanoid platform designed strictly for microgravity and orbital servicing. Developed as a spin-off from ETH Zurich, Helios features 4 symmetric arms instead of legs, using tendon-driven actuation to minimize moving mass and rotational inertia. On the artificial intelligence front, Google introduced Gemini Omni, a foundational world model that generates and edits high-fidelity video by embedding an intuitive grasp of physics like kinetic energy, gravity, and fluid dynamics. Google DeepMind also expanded Project Genie, combining its generative world model with Google Maps database of 280 billion Street View images, allowing users to play 3-dimensional simulations anchored in real-world geography.